Our next speaker is Shing Ho, who will tell us about Bayesian separation logic. Once his slides come up. Do you want to try speaking? See if it... Oh, it's not. Hold on one second. Can you try, see if his body mic works? Yeah?
Hello. Does it work?
No.
Okay.
Oh, it does?
Does it?
Can people hear him? Speak, say something.
Hello.
No.
Okay, I'll just use this one, yeah.
We'll just use the handheld mic. Yeah, I think the handheld is
useful. So hi, I'm Shing Hin, and today I'm going to be talking about our work on what's called Bayesian separation logic, which gives an axiomatic semantics to what's called probabilistic programming. And this is joint work with my supervisors, Azalea, Raad, and Nicolas. So to begin, let me first talk about, well, our goal of the project, and it's to reason about probabilistic programming using what's called probabilistic separation logic. So what's probabilistic programming? Let me illustrate this by with an example. So let's say, well, now, for example, if I found a coin on the floor, and I want to know, well, if it's a fair coin or not. So what can I do? Well, I can flip the coin and get back a bunch of samples, let's say C1 to Cn. So what we can do is to actually estimate, well, using what's called the Bernoulli distribution of x, which it returns 1, so that's heads, with probability x, and 0 with probability 1 minus x. So our goal is, therefore, to estimate x between 0 and 1. So if x is 0.5, for example, then it must be a fair coin because it returns 0 and head and tails with equal probability. If it's 0.9, then it's a biased coin towards heads because, well, it returns heads with 90% probability. And if it's 0.1, then it's a biased coin towards tails. So the key feature of probabilistic programming is what's called Bayesian conditioning. So suppose now I have a flat prior belief about my coin. So that's saying, well, I don't have much assumptions. X could be 0.75, or it could be 1. I have no prior belief, a flat prior belief about on this. Now, if I flip a coin, let's say if I get back heads, and I'll call the coin C1. So this changes my belief slightly because, well, now I have one sample, but I'm more inclined to believe that, well, it's more likely to return heads. So mathematically speaking, this basically updates my belief to what's called the beta 2-1 distribution, which basically says it's more likely to return heads. So if I do the same thing again, I flip a coin again, I get back tails this time, and I call it C2. So now my belief is shifted again to what's called the beta 2-2 distribution, which is to say that, well, it returns, well, I kind of think that's fair, but I'm not very certain about it. So because, well, out of all the samples I have, which, well, it's 2 samples really, well, one of them is head and one of them is tails. So probabilistic programming languages is basically a programming paradigm that allows us to express these models as programs. So given this experiment that I have, I can actually write this very simple program that basically runs and gives me back the beta 2-2 distribution. So the first line of the program says, I sample from my prior belief, which follows a uniform distribution on the interval. And the second line basically flips the coin according to the Bernoulli distribution that says, well, I return 1 heads with probability x, and, well, tails with probability 1 minus x. Now, if I condition on C1 to be 1, so that's with the observed construct, well, something actually changes. So before executing this line, I can sort of think of, well, the distribution of x being the unif 0 and 1 distribution. But after this, it actually changes my belief to what's called the beta 2-1 distribution because, well, I'm now slightly more inclined to believe that, well, it returns heads more often. So, well, at the end of this program, I actually get back the beta 2-2 distribution. So now, well, given this program, I want to prove some properties about this. Well, can we, well, reason about them logically? So for example, can I prove that expected value, so that's the average, is approximately 1/2? So, so this has a well-defined denotational semantics using what's called S-finite kernels. And we can always integrate this expression and get back 1/2. But can we actually do a line-by-line reasoning and get back some sort of Hoare triple that reasons about these programs and have a more high-level description of them? So this is basically the second part of the talk, which is about, well, reasoning about these programs using probabilistic separation logic. So what's probabilistic separation logic? So we know that, well, separation logic is basically a logic of computational resources, and probabilistic separation logic is the logic of random resources. So the syntax of PSLs is as follows. So we have the, on the first line, we have the standard separation, first order logic stuff that says we have conjunction, disjunction, some quantifiers. And for the second line, we have the probabilistic stuff, which says, well, the first one says that X is distributed according to a distribution P. And the second one says the expected value of X is some expression E. And the third and fourth one, well, are the separating conjunction and, well, the magic one, which is the Ryder joint. So P star Q in the case of PSL basically means that, well, P holds, Q holds, and also things in P and Q are probabilistically independent. So let me give an example. So let's say I have this proposition that says X is distributed according to a fair coin, star Y is distributed according to a fair coin. So what this means is that, well, this needs to be supported by something that basically flips 2 coins, because I can't say, for example, I flip a coin and call it X and negate the result and call it Y, because this will not be probabilistically independent, because if I know something about X, if I know that X is 0, then Y must be 1 in this case. So our work is called Bayesian separation logic, BASL. So it's a new model of probabilistic separation logic such that it's the first logic to support the observe, or more generally, the scoring construct in PPLs. So let's look at this example. So if I flip a coin and observe that the coin is 0, then, well, from a true precondition, I can actually prove that, well, the post-condition is that, well, the coin returns the Dirac 0 distribution, which means that it returns 0 all the time. And the second feature is actually dependencies during sampling. So if I have, look at this program, if I sample X and it follows a uniform 0 and 1 distribution, if I now sample Bernoulli of X according to C, so roughly speaking, we know that C is basically a fair coin in this case, but we can also talk about something else. So from a true precondition, we can say that, well, C has a conditional distribution that says if we condition on X being a certain value, then C will have Bernoulli of that value. So I'll illustrate the proof of these two features. So suppose we start from a true precondition, and we now sample, well, we flip a fair coin. Then there's this sampling rule, which is quite standard in probabilistic separation logic, that says from a true precondition, if I sample P, a distribution P, then the output variable X has distribution P as well. So this would mean that, well, we have a post-condition that says coin is distributed according to Bernoulli of 1/2. And now, well, if we observe that the coin is 0, then what we would get is, well, using our new observation axiom that says, given a precondition that says x is distributed according to pi, and if we observe p of x to be true, so p of x is some random expression, for example, then x has distribution L of p times pi, which in this case basically amounts to coin having the Dirac zero distribution, which returns 0 all the time. So this kind of intuitively makes sense because, well, if we condition that where the coin is 0, then it must return 0 all the time. And the second feature is the conditional sampling rule that says, let's say if we now sample x and it follows a uniform 0 and 1 distribution, applying the sampling rule again, we get back this that says x follows the uniform distribution. If we now say that, well, we sample C according to Bernoulli of X, then so this one's slightly more intricate. This is a slightly more intricate rule that says it's a conditional sampling rule that says given a precondition X is distributed according to P. Now, if we sample little p according to X, then we get back this a variable y such that, well, there's this new construct. Well, this is introduced in the Lilac separation logic, and it's called the conditioning modality, basically saying that, well, it says that, well, for every possible value of x, for almost all values of x, the little x, and we call it little x, and y has a conditional distribution that says p of little x is true, which in this case basically amounts to saying that for almost every possible value of my random variable x drawn from the uniform distribution, C has distribution Bernoulli of little x. So recall that we're trying to prove that the expected value of this program is 1/2. So now I'm going to show you how to do that. So we start from a true precondition, and we sample x. And if we now apply the sampling rule, then we get back x is univ of 0 and 1, as we've seen before. Now, if we sample C1 again, then by applying the conditional sampling rule, we get back a conditional distribution of C1 that says C1 is distributed according to Bern of x for almost every possible value of x. Now, if we observe that C1 is 1, we also have the conditional observation axiom that basically says that if I can basically do the observation, but conditionally on something, because I've conditioned that C1 is 1, then my post-condition says, well, for every possible value of x, C1 has distribution Dirac of 1 because we assumed that it's 1. So this is the tricky part of the proof. So I'm saying that, well, given this precondition, this conditional precondition, I can turn it into what's called the beta to 1 distribution, and with this theorem called the internal Bayes theorem, which is the main theorem of our paper. I'll explain this later, but so if we continue with the proof and say that, well, we sample Bernoulli of x from C2, and now, well, by applying the conditional sampling rule again, we get back C2 has distribution Bern of x. Well, we now observe that C2 is 0, and we get back, using the conditional observation rule again, that C2 has distribution Dirac of 0 now. And we now apply the internal Bayes theorem again, and get back x is distributed according to beta 2. If we now return x, because we know that, well, beta 2 is basically a primitive distribution that has expected value, or an average 1/2, we can show that, well, by the rule of consequence, we can show that the expected value, or average, is 1/2. So this completes the proof. So these are our proof rules. So I've explained most of them, and I haven't explained the frame rule and the return rule, but these are slightly standard things in separation logic. So another example I want to show is conditional dependency. So let's say if we now have 2 coins, let's call it X and Y. Then I get back a post condition that says X and Y have the distribution of coin, and they're independent using the frame rule. If I now say that, well, Z is X or Y, and I now condition that Z is 1, so what would happen now? So X and Y would be, well, no longer independent conditioning on this because, for example, if I know that Z is 1, and I know that X is 0, then, well, because Z is defined to be X or Y, then, well, Y must be 1 as well. So knowing something about Z and X gives me extra information about Y, so that's why it's no longer independent. And if we return X and Y, we can actually prove that the correlation of X and Y is actually negative. So what this means is that, well, if X increases, Y is likely to decrease, and if X decreases, Y is likely to increase. We have other features as well, such as loops, and we use it to basically prove things such as a clustering algorithm in Bayesian inference. And if you're interested in this, the proof is slightly long, but if you're interested in this, you can read our paper. So for the final part of the talk, I want to talk about the semantics of probabilistic separation logic. So the semantics is basically a stream of random numbers. So I spoke about how separation logic is basically a logic of resources, and probabilistic separation logic is a logic of random resources. So in the Lilac separation logic, they basically define it as a stream of random numbers, which is defined using what's called a probability space over 0, the unit interval to the power of n, which basically amounts to a stream of random numbers. And we extend this model to what's called a countably generated sigma finite measure space. So sigma finite measure space basically means that, well, we can have a normalized distribution as well, and we can talk about Bayesian stuff. And so countably generated in this case means that it's well behaved enough such that it forms a certain model. It forms what's called a partial commutative monoid, which gives semantics to separation logic. So our main theorem is what's called the internal Bayes theorem. So recall that I said, if I have these two statements, if I have a prior belief that, well, the coin is, well, I have no prior belief, the belief is flat. And if I now observe that I get back heads, then this is the same as saying, well, I have a beta 2-1 distribution. So the entailment, by implication, that goes from, well, the first half of it to the second side, and to the second side to the first side, the left-hand side of the statement. So this is justified, semantically justified, using this theorem, which basically says that we can do that. And the proof of the theorem is slightly intricate, and it relies on two things. The first thing is called the sigma finite disintegration theorem, and the second thing is called the existence of Barrow extensions. So what this means is that, well, if we have a stream of unnormalized random numbers, we can always have a random variable and take the conditional on it, which even when, for example, the random variable has measure 0 or probability 0, this would still work, and this is justified using these two theorems. So to conclude, I've introduced Basil, which is the first separation logic to support two things. The first thing is the observe and scoring construct, and the second thing is dependencies during sampling. And if you're interested, please read our paper, which also talks about, well, how the sigma finite model of probabilistic separation logic is defined, and also how it relates to existing denotational semantics. So that's the category of S-finite kernels. As for future work, we're quite interested in how can we define separation logic from a higher order continuous probabilistic programming language. as well as, for example, lean formalization, and how can we recognize our result in a proof assistant. So that's all. Thank you very much.
Thank you for the talk. I have a small question. When you mentioned that X is like X arrow, X capital, and you said it's for almost any value. You qualified several times. Can you explain why it's almost any value, not any value?
If I go back to the slide, when I said that X has so in this case, it basically means that for every possible value, for almost every possible value, so that means because I have a distribution in mind, so that's a uniform distribution. So for almost all values, simply means that, well, the probability of not drawing that things outside of that value is 0. So that basically means you can, for a first approximation, think of it as like for everything between 0 and 1.
Thank you for the talk. I was a bit confused about the beta Bernoulli example with a coin, because it seemed like the observe statement would also normalize the distribution. Mm-hmm. Is that the case or not?
So not really. So there's an existing denotational semantics, which basically allows you to express them as unnormalized measures, and that's needed because of a construct called score, which I haven't explained, which basically allows you to express some weird measures, such as the Lilac measure, which is not normalizable in the language itself.
So in the beta coin example, there should have been a factor before the beta distribution?
Say again, sorry.
So in the beta coin example, there should have been a factor in front of the beta distribution? Because it's not.
Yes, so I've kind of omitted this detail, but then we are keeping track of the normalizing constant in our logic as well.
Makes sense. Thanks.